paradise. Jungle. An artificial paradise. Paradise, 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 paradise.
Good afternoon, everybody. Welcome to class today. Thank you for joining me, whether you are watching live or you're watching the recording. I appreciate you just tuning in and watching and joining me. Again, if you're here with me live, we talked about this last week. You can go ahead and put questions in the chat as you have them. If you're watching the recording later on, feel free to email whenever a question arises, and we will answer that question as soon as possible. And so in Module 1, we are looking at history, right? And in looking at history, we are laying a foundation for kind of all of the other stuff that we're going to be talking about this semester, right? There are things that we're going to talk about in Module 1 and Module 2, even though they're not directly related to programming, web, and database foundations. There are things that we're talking about in the history module and in next week's module that we'll keep bringing up and we'll keep mentioning throughout the semester. Right? Because everything is kind of built on something. Nothing exists in a vacuum. Everything is built on kind of what came before it. And so when we look at the idea of history and kind of what we expect in the future based on what we know now, then, you know, we kind of see that, well, what we know now was built off of what was learned back then. What they'll know 50 years from now will be built off of what we're learning now. Right? Which still has that connection to the things in the past. So we have this through line of history throughout the ages, right, which is significant. And so in the interest of time, I'm going to kind of hit the high notes and hit the important things of our three histories: history of computers, history of programming, and history of the web. We'll spend some time in some areas where I think we need to spend some time. Even still, right, like the histories that we're covering are incomplete. You could do an entire class just based on one of these, right? And it would be full of information to kind of take in and learn and work with. And we're trying to do all three in a single week. All right, so we kind of have to pick and choose what we're talking about, pick and choose what we think is important in relation to, the kind of things that we'll be discussing. So in order to really properly discuss programming in the web, we have to start out with a discussion on the history of computers. Right, and so we're just going to have a really brief discussion of the history of computers here. But we basically start out in the very beginning here with this idea of the first computer. Right, and so our first computer, there's actually some disagreement as to what our first computer is. And this disagreement comes in based on the idea of the definition of a computer. And our definition of computer has changed over time. Right? What we once thought of as being a good definition for a computer isn't really a good definition of a computer anymore. Right? So we have one idea of the first computer here on this slide presentation that's based on a particular definition. And then we have another idea of a first computer that we'll talk about in extension from this. Right, so we need to think about the definition of the first computer. And the one that we have in our presentation here is a device that helps you compute. Right, we know the word compute. Compute has mathematical connotations. Right, when we talk about making computations, we're typically talking about conducting, math problems, right? So when we think of a device that helps us complete math problems, then the oldest device that we have that does that for us is the abacus. Right? When we look at the term compute, compute defined literally means to determine mathematically. So if we look at a device that helps us determine mathematically, then the very first instance of that we've seen is the abacus. However, our definition of a computer has changed quite a bit. Right, no longer are we in this space where we're like, okay, computer defined mathematically or determined mathematically. We can relate it back to the abacus. Our computers changed in terms of how we view the information cycle. So we can kind of look at this idea of the information cycle. Right? And so in looking at the information cycle, we're looking at the process of how data gets turned into information. And we can look at this in a couple different ways, right? This idea of how data gets turned into information. But our big deal here is that we are working with an input. Data is our input. Right? So we need some kind of input. We need to be able to run that input through some sort of process. And then on the other side of that, we get an output. Right? So we have an input. The input in this case being our data. We run it through some kind of process, which leads it to an output. The output in this case being our information. This comprises what we call the information cycle. And you might be wondering like what the difference is between data and information, because these are two terms that we use a lot, right? Information is data that has been processed. Data on its own is not valuable. Data on its own are just representations of characters stored as zeros and ones on a hard drive on a computer. But information, processed data, has value because we've taken that information, we've ran it through some sort of process, and now we've ascribed meaning to it so that we can use it in some other way. Right, so in terms of a modern day computer, what we're really looking for here is something that meets the ability to do this, to complete this information cycle, to take some kind of input and flip it around and turn it into an output. Right, run it through some sort of process and make it an output. And what this is, actually, might surprise you. Right, because we have one instance, right, when we think about the abacus, for example, right, the abacus is, from kind of the prehistory times, right, being used in old civilizations from way, way back. And our first computer that does an information cycle, like we're presenting here, also is older than you might think. Right? Because the first computer by the definition of compute being to determine mathematically is the abacus. The first computer defined as being something that can run the information cycle to take input, do a process, and produce an output is a loom. And let me just show you an example of a loom here. Including a specific type of loom, a jacquard loom. Let me get a good picture of one here, and then we'll pull it over. Here's an example of our loom that we're working with. Right, and so these looms, we're looking at them in terms of the early 1800s, right, when these came about, have a punch card that we can use to program them. So we can actually program these looms. You take a card, we'll see an example of a punch card in a bit. You take this card, you're able to punch out different spaces in the card, and you put that into the loom, and based on whether or not there are pins sticking up from the holes in the card, it produces a pattern in the fabric, right? So we have an input being the card that's put into the loom. We have the process, which is the actual weaving done by the loom. And then we have the output, which is the fabric created by the loom. So we see this concept of input, of output, with a process in the middle to make something valuable, nicely patterned fabric, as we kind of go through this, right? So that's the way that we kind of have these two definitions of computer, and how these two definitions of computer intermingle. Right, because really when we get into it, the first computer that we would actually consider a computer in terms of modern day standards kind of combines these two. right? It kind of combines these two things because we see something that is made to compute, something that is made to determine mathematically, but it's built on the input, process, output information cycle that was developed in, the creation of the loom. So if we look at this kind of going forward, this would be our first analog computer. Now, when we're talking about analog computers here, we're talking about pre-electricity. Right? When we get to the idea of digital, we're getting to the idea of binary. That's where digital actually came from, is that it's a device that processes digits as binary. But when we see the analog computer, and we'll talk more about binary here in just a minute and what that is and what that means. When we see the analog computer, we see this machine that was not run off of electricity. It was mechanical. And it was used to do math. 1822, Charles Babbage, the difference engine, kind of comes up with this, basically a glorified calculator, right? Able to do simple calculations. In 1833, Babbage kind of takes that to the next level, comes up with the analytical engine, which is the first programmable mechanical computer, and it utilized punch cards, like that loom we were talking about. Right, so somebody was able to take those punch cards, punch out the data in them, and then that would create a representation of data to the user that they could kind of save as, a program using this physical punch card. Now this punch card, we mentioned the punch card for the looms. The punch card looked like this. This is an example of a punch card. And so we see this punch card has these holes represented in it. And we have these numbers here, 0 through 9. You can see them kind of arranged up and down here. And we have these holes punched in here in different locations. So each row here is representing a bit of data. Right? If you know anything about, sort of computer architecture, you know that we have 8 bits in a byte. A byte stores 1 character. And then it expands into the other levels, right? Kilobyte, megabyte, gigabyte, terabyte, petabyte, so on and so forth. So each line on this card represents a bit of data being put into a punch card based program. Right? And we can see we either have a hole where what's beneath this card is exposed, or we don't have a hole where what's beneath the card is not exposed. So if we have little pins or something sticking up through there, if there's a hole there, then we can make contact. If there's not a hole there, then we can't. So this is basically how we used punch cards to program. And punch cards were used well on into the 1900s to write programs. A lot of different types of programming languages can be represented on a punch card. But obviously, the deeper we get into the punch card, right, the bigger this idea of, the bigger stack of cards you'd need for the more advanced type of program you'd want to have, right? So we kind of needed to come up with a system to be able to, make these programs a little bit easier to handle. But the big thing that we get out of the punch card here is the concept of binary. So we actually get the concept of binary from looms way back in the early 1800s, 18 yada yada, right? Pre-1822, pre-difference engine. So that they could be applied in the analytical engine. And so our concept of binary comes from way back. Either we have a whole or we don't. Which would be the same as saying, we have a 1 or a 0, a true or a false, an on or an off. Right? So this is our concept of binary. Binary is a base 2 number system. And it consists of only two numbers, 0 and 1. We use a base 10 number system normally. It's called decimal, right? Our regular number system that we use is a base 10 number system. It's called decimal. It gives us numbers 0 through 9. Right, and when we look at our numbers, each number has a different place value. Right, so if we look at the number, let's say 1284. 1284. Each of these numbers has a place value. Right, we have a ones place, a tens place, a hundreds place, and a thousands place. Well, in binary, we have place values as well. What's interesting about binary is that when we look at a number, for example, like we would in decimal notation, each place is the base number of the system raised to a subsequent power. Right, so our ones place is 10 to the 0. Our tens place is 10 to the 1. Our hundreds place is 10 squared. Our thousands place is 10 cubed, and so on and so forth, right? 10 thousands is 10 to the 4th, 100,000s 10 to the 5th, millions 10 to the 6th, so on and so forth, right? Well, binary is set up the same. If we look at binary, we have the same sort of base, but now our base number is 2 instead of 10. So we start out at 2. And it's 2 to the 0, 2 to the 1, 2 squared, 2 to the 3rd, 2 to the 4th, 2 to the 5th, 2 to the 6th, and 2 to the 7th. And those are all we're going to concern ourselves about for this course, because that's all we need. That's our octet. Right? We have 8 bits of binary data here. 1 byte. And we said 1 byte stores a character. So 8 bits in a byte. Each one of these places is a binary digit or bit. And all of them together put into what we call an octet is a byte. And so if we extrapolate these out, we can talk about the place that they are, the place value of these things that they are. Right? So like if we look at our decimal here, we have our ones place, our tens place, our hundreds place, our thousands place, 10,000s, 100,000, so on and so forth. Well, in binary, 2 to the 0, anything to the 0 power is 1. So we have a ones place, right? Just like we have a ones place here, because anything to the 0 power is 1. 2 to the first, anything to the first power is itself, so we have a 2's place. 2 squared is 4, so a 4's place. 2 cubed is 8, an 8's place. 2 to the 4th is 16, a 16's place. 2 to the 5th is 32, a 32nd's place. 2 to the 6th is 64. a 64th place, and 2 to the 7th is 128, a 128th place. And so we basically see we're basically doubling the number each time, right? Because we're taking the number before it and then multiplying it by 2 again. Right? So we're taking the number and we're doubling it each time. And so until we get to that 2 to the 7th place, which finishes our octet. Now, why is this important? Why does understanding binary for our purposes become important? I could talk for the rest of the hour on this, right? Just this alone. So I'm going to try to do this pretty quickly. But it becomes important because we said that's the way that our computer recognizes things. Right? Our computers don't see letters and numbers. They don't understand things. Right? We, as human beings, are smart. Our computers are dumb. Our computers don't understand the difference between different characters. All they're seeing is they're seeing a different set of bits being passed through that it has to process into information. Right? So it takes the different bits, it runs it through a process, it takes the data, runs it through a process, turns it into information. Then we see the information and we ascribe meaning to it. Our computer doesn't know what any of it means. Our computer doesn't know that this is the word decimal or that this is the word binary. It might know the sequence of bits that it needs to make that into a representation, but it doesn't know what these things are. Right? So this binary becomes important when we're looking at something called an ASCII table. This is our ASCII table here. And we can see the different values that we have for different characters. All right, and of special notice is this section on the right-hand side over here. We'll zoom in so you can kind of see these. Uppercase letters and lowercase letters have two different decimal values. Right? So for example, if we look at the letter B here, you and I see the uppercase letter B and the lowercase letter b, and we can see anything that's, has that letter in it. We know, okay, that's a B, and we can read it accordingly. But our computer doesn't see that. Our computer sees the calculation of the decimal value on this chart converted into binary. So when it sees an uppercase B, it sees the binary value of the decimal number of 66. And when it sees the lowercase b, it sees the binary value of the decimal number 98. It doesn't know what a B is. It just knows the characters that we give to it. So it sees a lowercase b as a 98. It sees an uppercase B as a 66. These are two completely different things. Right? And this all came back from that, this all came stemming way back from the loom and the analytical engine from the 1830s, right? This concept's pushed forward. So when we get into programming, one of the big key things is that we have to know how to be specific. We have to know that if we're supposed to use a lowercase letter, we have to always use a lowercase letter. Because when our computer sees a lowercase letter, it doesn't know what that letter is. It just sees the representation of that letter. Our computer's dumb and we're smart. Right? We can take this a step further. Yes, so we know we have our B values here, right? We have a uppercase B and a lowercase b. And we can actually go so far as to calculate them. So we know that our uppercase B is a 66. So if we wanted to convert that into a binary octet, we know we have a 1's place, a 2's place, a 4's place, an 8's place, a 16's place, 32, 64, and 128. So we start all the way over here on the left. And we say, okay, 66 minus 128. Does that give us a positive number? In this case, it does not. It gives us a negative number, right? So we put a 0 here. 66 minus 64, does that give us a positive number? Yes, it does. So we put 1 here. And then we can subtract 64 from this, which leaves us with 2. And so now we're working with this 2 because we have our 64 here represented by this binary digit. And so we just have to go down the line from here. So no 32, no 16, no 8, no 4, yes 2. And at that point we have 0, so nothing else works. And so when we look at our uppercase B, what our computer sees is 01000010. That is the byte of data our computer processes to see the uppercase B. The lowercase b, on the other hand, we said that value was 98. So this first number is still 0 because 98 minus 128 gives me something less than 0. So we put a 0 here. 64, we can work with that. So that gets a 1. And that leaves me with 34 here. So we can put a 1 here. So that's 32 subtracted there. Then we're left with our 2. So we can say 0, 0, 0, 1, 0. So to represent a lowercase b, our computer doesn't see lowercase b. I know what a b is. Computer doesn't know what a b is. It sees 0, 1, 1, 0, 0, 0, 1, 0. Which means the only difference between an uppercase b and a lowercase b is just this one singular bit of data in the 32nd place between these two binary octets. And that single difference seems so trivial, but it is so important when we're talking about writing programs. Because our computer doesn't know uppercase versus lowercase. It knows this character versus that character because they're referenced by different strings of data. So even one bit being different, like we see right here, means the difference between our computer understanding what we're talking about and not understanding what we're talking about. And we've been doing this since the early 1800s. We've been working with this concept since the early 1800s. And just as kind of an interesting aside, many of you might have seen like this symbol here, where it's like a line through a circle on power buttons. And that's actually a representation of binary, because it is a 0 and a 1 put together. And they put it on power buttons because your computer has a binary state, or anything that has power takes power, has a binary state. It's either on or it's off. Because when we really break it down, that's all we're talking about here, right? Because our computers don't even really understand numbers like this. It understands electrical impulses. So the way our computer actually understands binary data is even more primitive still than just the idea of 0 and 1. It's the idea of pulse of electricity or not pulse of electricity. Creating sort of a weird Morse code out of the signals that's being sent through a digital computer, right? Because that electricity represents a binary digit, which is why we call it digital. So we use this ASCII chart for that. Now, our first analog computers here, they weren't great. The Babbage engine, the difference engine, the analytical engine, not great, right? Pretty bad, actually. The amount of parts that were in them made manufacturing prohibitive, right? We kind of get one kind of proof of concept working model, kind of halfway. But if we wanted to mass produce, it was basically impossible. Since we are talking about a mechanical computer, the amount of slop, right? The play between the parts, anything that we make mechanical, since we're making something that we have to like use gears and levers and pulleys and all this kind of thing for, just the nature of friction and the inconsistency in the manufacturing of parts meant that an analog computer was not very precise, right? It means that we could put the same problem in a computer multiple times during this time period and get a different answer, right? Which is very much less than ideal, right? And we see the idea of these mechanical computers continuing on into the 1900s, right? The analog computer was the big thing on into 1927 when we got Hazen and Bush's differential analyzer, our last major advancement in that sort of way. So from analog, we moved into digital. And these are electromechanical. So now we have electricity that's being utilized here so that we can represent a digit using electricity, right? That's where we get digital from. We can represent a 0 or a 1, a pulse of energy to represent a 0 or a 1. And any data that was processed electronically at this time was processed using vacuum tubes. And we see a picture of some vacuum tubes here. Look kind of like, old school light bulbs. Right, and the thing about these is that like light bulbs, these things would burn out. They'd bust. They'd go dead. I mean, they're made out of glass, and there's a vacuum pulled inside of them. So they're fragile. So they could break. But guess what? There are hundreds, if not thousands, or tens of thousands of these being used in a singular computer at this time. So just imagine being the person that would have to go in there and change one of these if they were to go out to replace them. I mean, first of all, it's going to just halt production completely. But second of all, imagine trying to find the right one when there's thousands of them. And imagine how big something would need to be if it had to have, thousands of something the size of a light bulb in it. That's pretty big. Right, now you can see the dates here to when we finally moved into purely digital computers, away from the electromechanical on into the purely digital, using more and more of these vacuum tubes along the way. In the 1930s and the 1940s. Now, what was going on during this time period that would make this so important? Maybe World War II. Right? So when we think about World War II in this sort of way, and what a digital computer would mean for the war effort, it's immense, right? Like when we were talking about the mechanical computers and when we were talking about the analog computers, I mean, what did we just say? Analog computers are imprecise. You could put the same problem in an analog computer and get multiple different answers because the parts aren't machined together perfectly. Right? And then there's friction and there's all this other sorts of stuff that plays in here. So you could put in the same problem, get different answers out. Which is all well and good, but you want to know what one of the tasks utilized to using mechanical computers was before we got these digital things? Determining bombing trajectories. So if you have a target and your target's in one location, right, your target is typically not moving, right? It's a sedentary, it's a building, it's some sort of facility, it's whatever. If you've got a target and you know precisely where that target is, and you do the calculation, and you do the calculation 6 times, and you get a slightly different answer each time you do it, this is something where precision means a lot. Right? And so slight variations in calculations could mean the difference between hitting your military target and hitting the hospital a few miles up the road. So having the need for precision here becomes incredibly important. Another big thing that was used during this time is the idea of code breaking, right? There was a lot of code talking that was used during this time because, we had radio signals here, communication across the airwaves, but, a radio signal is only as good as, your enemy not knowing which channel you're broadcasting on. But if you talk in code across the airwaves, then, your enemy may or may not know what you're saying. So when codes were changing and things were moving really quickly, to try to break these codes with a mechanical computer would be nearly impossible, right? Because you'd have to break it down to parts and readjust it every time a new code would come about, or you'd have to build a completely different thing. Whereas with our digital computers, it would take some time to do some rearrangement, but we'd be able to, adapt to the new codes fairly quickly. And so we saw 2 computers here that, are aiding in the war effort. One of them is from the United Kingdom. The other is from the United States here. We have the Colossus and the ENIAC. And I believe in the module I also talk about the UNIVAC. But when we see the Colossus here, we see 1943, the first electronic, digital, programmable computer, right? United Kingdom. And it was primarily used to break those codes that we were talking about. The ENIAC, later in the year, later in 1943, faster and more flexible than the Colossus. And it was able to be programmed through patch cables instead of punch cards. right? The same idea was still at play there, right? When you think about patch cables, you can kind of see an example here. Like if you've ever seen like, maybe old movies or old television shows where they have the operator switchboard and you call the operator and you say, oh, put me through to wherever. And they take the plug out of one hole and put it in another hole and they transfer you over. We can kind of look at them like that, or, it's kind of like a 1/4-inch guitar amplifier cable, right? You're just bridging that connection. And so the same principle behind this was still at play, right? Either the patch cable was in place, which allowed electricity to flow from one element to another element, or it wasn't there, which broke the circuit. But an interesting thing about this is just how much this weighed. Right, and so our answer here for how much this thing weighed is 30 tons, 60,000 pounds. It used 200 kilowatts of power per hour, which is wild, and had 18,000 vacuum tubes. Right, so again, imagine having to change one of those. But the big thing here, 30 tons, 2,000 kilowatts of power, which is a lot of power, 18,000 vacuum tubes. It could perform 5,000 calculations per second. Which at the time, 1943, mind-numbing speeds. The iPhone 6, which is now, 6 iPhones old. Just about, right? Can do 3.3 billion. When we looked up the iPhone 13, I believe it was like 4 trillion calculations per second. And that's something that you can put in your pocket. Something that you could put in your pocket versus something that was 30 tons. That's insane. Right? That's incredibly wild. So let's go pretty quickly through a lot of this material. The idea of the modern computer was actually developed before we really even got a digital computer, right? It was developed by Alan Turing in 1936. He proposed the idea of the universal computing machine in a paper called On Computable Numbers. And when I think about Alan Turing is one of your choices for a figure to write your paper on. He was really a mind ahead of his time. Some of the things that Alan Turing was writing on during the 30s and 40s and 50s were, things that we're just now starting to get a grasp on today, right? Like the idea of neural networks and machine learning and artificial intelligence. Like these are things that we're just now really getting going, and Alan Turing thought of them, 70 years ago or more, right? But basically the idea was that the modern computer relied on the invention of 3 new components. One was the fact that we needed stored programs. Well, we got those in 1948. We didn't have to wait long for those. But if you needed to change the programming of a computer, you had to reconfigure it completely prior to 1948. Right? You had to rewire it. You had to get a new set of punch cards. You had to do some big effort. Imagine having to take your computer apart and put it back together to do a different program today. It'd be absurd. Right? We needed stored programs that allowed instructions to be read from memory. And so in 1948, we got the very first one, the Manchester Small-Scale Experimental Machine, which was called Baby. This was the first stored program computer. Transistors. Right? We needed something more effective, more efficient, that can be better than vacuum tubes. So not only is that going to be more energy efficient, less hot, right? Imagine how much heat all those vacuum tubes represent creating, right? So it's going to shrink the computer considerably. The first transistorized computer was developed in the University of Manchester in 1953. integrated circuits, the idea of the integrated circuit, aka the microchip. So you take multiple of these transistors and put them into small electronic circuits on one piece of semiconductor, a motherboard, for example. So now not only are things getting smaller, but we're starting to make things mass producible, right? We can build machines that can handle this, and it starts to become more reliable. And we get the first practical integration of this by Jack Kilby and Robert Noyce. And when we get into the idea of the post-computer, which is the last slide here, that's essentially mobile devices. To save ourselves time, let's move on to the history of programming, which is this one. Nope, that is the same one I just had. That's this one. History of programming is this one. And so this looks like a lot here, but we can actually breeze through a lot of these first couple of bubbles because we've already talked about them. Right? The idea of pre-programming. 1801 is when we got that Jacquard loom that I showed you earlier. That gives us the foundation for where we're performing that data cycle. And then Babbage used it in the analytical engine in 1833. The idea of the punch card, right? We already looked at binary. We already looked at punch cards. We already talked about all of this. It's also in your module as well. So we'll just fly right by that. The first programmer is very interesting because it is another one of the individuals that's on your list of figures for the potential of completing your lab paper on. The first programmer was Ada Lovelace. Ada Lovelace is considered to be the first computer programmer. So, ladies, that's a feather in your cap, right? The very first computer programmer was a woman. And more than just that, she was absolutely brilliant. In the seated class, those who wrote about Ada Lovelace, many of them stated that her greatest contribution was just her mind and just how brilliant she was. And I'm not inclined to disagree. Right? I mean, this is the very first person who was taking something that was already an abstract concept, right? These higher level mathematical thinking problems, right? And she converted them to punch cards to be ran through the analytical engine. The level of understanding of the math that would need to be done in order to do that conversion is absolutely incredible. And even more than that, I think we see the forethought that we have here, right? She theorized that one day the computer would be able to play music and chess. And now our computers are primarily used for entertainment and video games. If we had more time, I'd talk a little bit more about the gravity of the algorithm that she wrote here for the Bernoulli numbers. Just go ahead and look up the Bernoulli numbers when you get time here and what those are and the calculation that has to go into them. And that'll be even more impressive that she was able to take that algorithm and put it onto punch cards. Herman Hollerith developed the plug board. So in 1906, he developed the plug board, also called the control panel. It was the successor to the punch card. Right, we've already mentioned that, still based on the same idea of binary as the punch card, plug in, port on, plug out, port off. So it was a way to program the computer and reprogram the computer for different tasks without the machine having to be completely reconstructed. And it was the forerunner to computers like the ENIAC, like we've discussed, right? And really kind of changed the direction of computing in the 20th century. Now, Herman Hollerith was the founder of a company that you might recognize, a company called IBM. In those days, his company was called Tabulating Machine Company. The Tabulating Machine Company would later become International Business Machines, or IBM. So IBM, the company that would become IBM, was founded in 1896. You know, it's kind of like the old, if you've ever heard of the company that was, when Nintendo was founded, Nintendo made playing cards, right? And then they moved into video games. IBM was the Tabulating Machine Company. They made mechanical computers in 1896 for the purpose of, doing simple calculations, simple computations. And that evolved into IBM, International Business Machines. Computer bug. The first computer bug was discovered by Admiral Dr. Grace M. Hopper, another of our significant figures. Dr. Hopper was another person who contributed a great deal to the field. And in these times, a bug was an actual bug, right? Like we said, in this case, we're talking about a ship. We're talking about a relay calculator on a naval ship. A mechanical computer, right? Like we were talking about, we're going to calculate trajectories and we're going to do all this sort of stuff. We need mechanical computers. And so if a bug or if something gets in there that's impeding the parts from meshing with one another, then it'll stop it from running. And there's actually a picture of the first computer bug. I didn't put it in this presentation, but I can grab it over here really quickly. This is it. It's a moth. We can see it taped there to the logbook, thanks to, the military's great what's the word I'm looking for? Documentation of things, right? We can see what it was, moth, where it was, relay number 70, panel F, moth and relay. Right, just an interesting, fun little story there. It's where we get the term computer bug from, is the idea of, there being an actual bug in our computer. We'll do just a little bit more, because we're running up against time. For the things that I didn't cover here, right, there are videos in the module that cover it. High-level programming, let's talk about what high-level programming is. So the first high-level language that was developed was Fortran. And it was developed in 1954 by John Backus. And when we say what makes a programming language high-level, is that it's more close to English. Right? Remember that our machine thinks in that machine code. Our machine thinks in binary. We don't think in binary. Right? We need a language that we can understand that can get interpreted into binary. So high-level programming languages are more user-friendly. They're closer to English. The further that we get from pure machine code or binary, the closer that we get to a language that's spoken by human beings, the higher that level is considered. The higher level that language is considered to be. So when we get into Python in a couple weeks, we'll be working with a high-level programming language, because we'll see that it's very close to English. This is what a hello world looks like in Fortran. I don't think we'll get to the other hello worlds today. Maybe we'll run through them quickly. But a hello world is just a very basic, simple program that everybody kind of writes as their introduction to programming in general, right? Sort of a hello to the world of this programming language. But we can see that here. And you know what? I think I want to end on the first computer game here because I think there's something interesting to this. And it's something that really kind of gets a little bit existential when it comes to the idea of programming and creating things and working with things. Right, in 1961, we see the first two-player game where spaceships fire at one another. Right, it's played two players on the same keyboard. Right, no such thing as an online game yet. Two players on the same keyboard had spaceships that would fire at one another. It was called Space War. And it was created by Steve Russell, 1961. Took him roughly 2,000 hours to program. But this was before the time of easy monetization of software. So Russell never made any money from the game. And I think his quote here is pretty pertinent. Right? He says on Space War, if I hadn't done it, someone else would have. Someone would have done something equally exciting, if not better, in the next 6 months. I just happened to get there first. And I think you can look at this in one of two ways, depending on how you look at, life in general. And this is where we'll wrap today up. Because in one sense, he's saying, well, if it wouldn't have been me, it would have been someone. So why not me? Why not work on it and get there first and be the first person to create this computer game? Why not work on this and do it? Make something from nothing. Make something where it didn't exist before. I think that's a very positive spin you could put on this. Conversely, you could look at it as Russell saying, well, I'm kind of irrelevant to the situation. Because if it wouldn't have been me, it would have been somebody else. Somebody else would have come along, made something very similar, if not better. And so the fact that I did it is kind of insignificant in the grand scheme of things. When we think about that in that sort of way, there is a lot there. So it's just something to kind of leave you thinking about here for the next week. That's where we'll end for today. We'll play the music. I'll stay in chat for a minute just in case anybody has any questions. All the other stuff that we didn't cover here is covered in a video in the module. Thank you for watching. We'll see you next time.